Greetings. In past videos we showed various options on how to talk to your house. And a couple videos ago we showed options on using your computer monitors, your TVs, your tablets, your phones, on how to look at what your house is saying. Today's video we're going to talk about how to listen to your house. That's always good parental advice. Be a good listener. I'm going to use this Z-Wave remote from Aeon to simulate the house saying something.
Someone is at the front door.
Someone coming to our front door. So that's option one. We have a small little black round USB speaker over there plugged right into the home automation system. Works well if you're in the same room or maybe a neighboring room, but if you're several rooms away or downstairs or outside, you can't really hear it very well. For example, say you're lounging in a treehouse.
Hola, this is me trying to lounge. So our treehouse is about 100 feet away from the house. So as you might expect, you can't hear that little round speaker at all. So enter option 2. Use your cell phone.
Someone is at the front door.
Which is in my pocket. So get that out of my pocket and show you again. You send the text, you have your house, send the text to the phone.
Someone is at the front door.
And then use Tasker or something similar to spit it out to your phone's text-to-speech engine. That works pretty good, except for the cases where you have to explain to people why your pocket is talking to them. Or if you don't have your phone with you, like if you're around the house, I usually don't have my phone with me. So enter option 3.
Someone is at the front door.
Put a speaker in most of the rooms of your house, at least the ones that you frequent. Now 15 years ago, when I was first getting into home automation, I did this using a PA amplifier and a PA speaker in every room in the house with a relay board that picked which rooms got spoken to and a whole bunch of Cat5 wiring. Big pain, kind of expensive. Today I'm going to show you how to do it for about $60 a speaker using Wi-Fi and a Raspberry Pi. So up here, above this fairly ineffective carpenter bee trap, in that plastic box we have our Raspberry Pi, and next to it we have an inexpensive USB.
Someone is at the front door.
It's like a $8 USB speaker. So I set the loudness to that such that I can hear it from, I don't know, about 50 feet away.
Notice device 2. Mqtt is down.
And you can just hear it talking to us, but not so loud that it bothers the neighbors. I have another one down there underneath the deck, so that if I'm closer to the house, that one I can hear. From here you can hear, you can still hear the treehouse one, but you can hear this one a little bit louder. So go inside and we'll show you a little bit more about the Raspberry Pi hardware, and then talk about the software that we use. They use a protocol, really handy, fairly popular protocol called Mqtt to send the speech over the Wi-Fi to all the speakers. So this is one of those displays I showed you a couple of months ago where we have it set up to display photos, recent house speech, temperature, humidity, weather forecast. Used to drive it with a Chrome stick, and I replaced that with this cute little Wally-like setup, which is a Raspberry Pi driving a USB-powered speaker, which is good, loud enough for a room this size.
Someone is at the front door.
But the advantage to this has over the Chrome stick is that it can drive not only the display and the speaker, but we can also hook into the GPIO port various things like this $5 temperature humidity sensor. This hooks right into the ports and replaces those Arduino Unos that I had scattered about the house. I still have one up there. The advantage this has over the Unos is the multi-purpose, and it's actually cheaper. The Unos were $60, this is $35. About the same power, around 3 watts. And they're very popular. So next time I'm going to show you the house speaking to every room that I have set up. I have about 6 rooms by running this test. Alexa, ask house to run speech test 1. So first it'll speak to every room in the
Hi
house.
there, room all.
Then it'll speak to one at a
Hi there,
time.
room Bruce.
There,
Hi there, room upstairs.
over here, then in the bedroom, then the downstairs, and back into the kitchen,
Hi there, room kitchen.
and then out to the treehouse. And then all the rooms again at once.
Hi there, room all.
So the trick to that, well, before I show you the trick, let me just quick show you the various speakers. So hiding behind this plant, we have another Pi, this time in a translucent case. It's driving a slightly different set of speakers.
Someone is at the front door.
Also about $10. And in this room, you can see we have another guy using one of his bigger speakers.
Someone is at the front door.
We have a lot of people visiting us today. You see another temperature sensor hiding out back there. So the last speaker we have here hiding under the deck, it's another one of these big
Someone is at the front door.
$8 speakers. I don't know how weatherproof these are, but at $8 a shot, I can afford to experiment. Let me show you real quick the this case. We just put a little notch in the corner here for the wires to run out. And if you get a right-handed USB connector, it fits just fine here. And you can put the power brick in here if you wanted. I run the power brick over the outlet there. So I think that's all the speakers I have. In addition, I can drive any Windows computer, like the one at my desk, with the same Mqtt Perl code that's on the Linux and Pi computers. So I'll show you how that works next. Doggy here, the quick public service announcement. What are you growling at? The rest of this video is going to be pretty dry. It's going to be in the technical weeds of how we get this MQTT protocol to synchronize these speakers. So I suspect most of you will want to call it quits here. We'll call it good for now. See you next time. So MQTT was a lightweight protocol developed by fellow IBMer Andy Stafford Clark and Arlene Nipper about 7 years ago, for especially useful for Internet of Things, where you want low bandwidth, low power devices all communicating to each other. So you have a broker, kind of like a server. He can be either on your internet or your internet, and he receives data from sensors or other clients, and then he passes those on to clients that have subscribed to that data. So in our case, we're going to run broker on my Linux box. I'm running Mosquito. There's a bunch of them out there. You can pick your favorite installer and just install one of them. And then we're going to take some Perl code and modify our text-to-speech code that we presented a couple months ago, where we use the IBM Watson server to generate speech from text. And we're going to have that text-to-speech Perl code publish the actual WAV file to the broker. So the broker doesn't care whether it's binary data or text data. This example is text, but in our case, we're going to send binary WAV files or MP3 files. And then each one of our 7 speakers is going to subscribe to that broker. And once the broker gets the WAV file, he'll send off the WAV file to each of the 7 devices. Now here's where it gets tricky, because in order to synchronize the devices so that they play the speech at the same time, we have a simple protocol developed where we send the WAV file out to the clients. The clients then send back a speak ready indicator, which means they've received the WAV file and is ready to play it. And then when the client detects that all of his fellow speakers have all received that file and are ready to play it, then they will play the device, and then they'll send a speech done indicator back to the broker so he can keep track of things. Well, that sounds confusing, but let me show you how that works. So this is just to show you that I have 2 different daemons running. One is the broker, which is Mosquito in my case, and the other is this text-to-speech MQTT client. Before I show you that, I will show you the TTS code. So this is a modification to the text-to-speech Perl script that we showed you months ago that took the Watson speech synthesized file, and now instead of playing it locally, we're going to send it to our MQTT server. Here's an example commented out of how you would use the Mqtt publish utility to send it. We would send it with this topic, and that's the file that points to the synthesized speech file. Instead, we're going to use a Perl function called Mqtt simple. That gives us a few more options. So we hook it up to our broker on this server. Then we read in the file. We open the file up in Perl and we read in the data to this variable. Then we do a simple lock in case we're trying to play two files at once. We'll make sure we wait until the previous file is done playing before we play the next one. And then we're going to tell the MQTT broker that we are sending this speech data. Then we're going to sleep for a little bit, and then as a backup, in case all the clients don't report in, we're going to send this backup flag, resend the data so we make sure that it gets spoken. So now I'll show you a handy Chrome extension that will be a useful way to monitor the network to help you understand and debug all this data. So it's a Chrome app called Mqtt Lens, and you just create a connection to wherever your server that your broker's on. Then you subscribe to the topics that we've created, which are MH, speak, send. So subscribe to that topic. Then we'll have a couple other topics when it's ready. Subscribe to that one. When it's done, subscribe to that one. And when it's the backup one. So hopefully we won't see any activity there. So now this is ready and it's monitoring the network. So if we go back and send some speech over the network, we'll just say hello.
Hi.
What we see then is our speak send topic got the message in binary of that hi file. And then what we see in response is each room reports as they get the data. There's downstairs, there's kitchen, there's treehouse, there's deck, there's bedroom. Each one of them are reporting in that they've received the WAV file and are ready to play it. Then the clients will detect this because they've subscribed to it. And when they see all their fellow speakers have reported, they'll go ahead and play the WAV file. And that way we're guaranteed that we're fairly synchronous in all, independent of whether one speaker's slower or faster than the other. Then when they're done, they report back again and say they're all done. Then we send a backup in case the speech didn't work, then they'll play this backup file. So finally we'll look at the TTS client code. And you'll see it's another Perl script, and there'll be links in the blog post to this, so we won't go over this in detail. But the gist of it is right here. This client will subscribe to when the data is sent, and this, when it's sent without a room, all clients will speak it. When it's sent to just a particular room, just this client, the one that matches that room, will speak it. Then when the data is ready, they will detect that, and you can see what we're going to do is we're going to play the file. Here's a simple case where it's just sent to this room alone, so we don't need to do that synchronization, and we just write the file out and we play it with a player, whatever client is appropriate for that platform. And this is a case where we're sending it to multiple rooms, so we want to be synchronized. So it will first receive the file, write it out, and then it'll publish that I'm ready to play. I've received it and I've written it. And then once all the rooms it's detected that all the rooms have received the file, then it'll play it. One reason that the rooms can be, one room can be slower than the other is because their Wi-Fi speeds might vary. You might have one room that's further away and it has a weak Wi-Fi signal, and that's why it's slower. So in addition to having the Pis report back their various temperature and humidity data, I have them report back their Wi-Fi strength, so you can see which rooms might need a better Wi-Fi connection. So here you can see the bedroom's a little weaker than all the other rooms, and the kitchen is the strongest connection. Finally, one other trick that I use is we monitor when each of the speakers reports that it's done. I have this special client that reports what the latency difference is between the various rooms. So in that last speech that I sent, you can see that the downstairs was the fastest and the deck was 200 milliseconds slower. If I saw this was consistently slower by much more than this, then I would adopt the code, and there's a hook in there I have that we can put speech in at various, to account for latencies. For example, if you have a Bluetooth speaker, you need to put a latency of about a half a second because Bluetooth buffers for that much. Whoa, some of them actually made it to the end. I'm impressed. Bye-bye.